Let's talk about truth tables and the logical operators. So what we're going to do is I'll introduce some of the mechanics of the truth table as we're talking about the logical operators. Now today I'll probably just cover in this video, I'll probably just cover one of the operators. We'll cover AND since that's the easiest, maybe negation as well. And I hope that'll give you a feel for how the layout of the truth tables works. We're going to be talking about AND, as we've seen already. AND is the operator that holds together the two parts of the sentence, or parts of the conjunction. So a conjunction is a joining together of two declarative sentences. So declarative sentence 1 here is Groucho has a mustache. Declarative sentence 2, George has a pretzel. And what we can see is, well, here we've got this logical operator. It's set up such that we can conclude either 2 or 3 given 1. So given 1, we can conclude either 2 or 3. 2 being Groucho has a mustache, 3 being George has a pretzel. So as we've seen, we've studied entailment, and we've seen how 2 and 3 would be entailed by the conjunction 1. Okay, simple enough. So it's a valid piece of inference, or it's a valid inference from 1 to either 2 or 3. Okay. You can conclude 2 from 1, you can conclude 3 from 1. So we've seen already that what we're going to do is we'll give variables for each of the declarative sentences. So a variable here, the variable P stands for some declarative sentence. That declarative sentence can be true or false. So there are two possible ways of being true or false. P can either be true or it can be false. So for any declarative sentence, a declarative sentence, again, remember, is a sentence that's saying something about the way the world is. Declarative sentences are either true or false. They have a truth value. For any declarative sentence, there's only going to be 2, true or false, given what we're talking about in this class. Now, if you have 2 declarative sentences, P and Q, Q standing for another declarative sentence, and you want to know in what ways can they be true or false together, then what we see is that there are 4 possible ways for P and Q to be true together. And what we have here with this truth table is a representation of those 4 possibilities. So if we look at, here we have let's say, the column falling under P, and consists of 4 possible truth values, combinations of T's and F's. So let's look at each one of them. 1, 2, 3, 4. So we'll label the rows 1, 2, and 3, and 4, and we'll look at what's involved at each step. So in the first case, P is true and Q is false. So going back to our earlier example, this would be the case, let's say, where if we have P here and Q here, in the first case, Groucho has a mustache is true. George has a pretzel is true. We're not looking at the AND yet, we're just looking at the 2 combinations. Let's look at the second case. This is the case where George has a mustache and Groucho has a mustache rather, and George does not have a pretzel, or it's not the case that George has a pretzel. So here we'd have the false. Let's go to our cleaner version here. So case 2, Groucho has a mustache is true, as it was here. But in this case, George has a pretzel is false. So it's not the case that George has a pretzel. This is how we're representing it here. Q is false. But it is the case that Groucho has a mustache. Okay, let's look at the next possibility. The next possibility would be that Groucho does not have a mustache, or it's not the case that Groucho has a mustache, but it is the case that George has a pretzel. And then finally, the fourth possibility is that Groucho does not. It's not the case that Groucho has a mustache, and it's not the case that George has a pretzel. So these four ways represent the only ways that P and Q can be true and false together. They exhaust all of the possible combinations of truth value for these two declarative sentences, or for any two declarative sentences. So these are all the possible ways that two sentences P and Q can be true and false together. So once again, just in terms of the mechanics of this thing, when we look at the how we represent the rows, the rows here, let's say this is a row, this is a column. Up and down is a column, left and right is a row. So the columns, right, represent the combinations. The rows represent the value for each of the separate propositions. So here we've got the case where P is true, the case where P is true. Whoops. How do I do this? There we go. So we've got the case where P is true in 1, the case where P is true in Q, the case where P is false in 3, and the case where P is false in 4. So the case where P is true, the case where P is true, 1 is true, 2 is true, 3 is false, 4 is false for Q. Now if we look at for P. If we look at Q, Q is true in 1, Q is false in 2, Q is false in 2, true in 1, true in 3, and false in 4. So you might notice that there's a sort of a conventional arrangement of the columns such that we've exhausted all of the possible ways for these two declarative sentences to be true and false together. Namely, when we look at each of the columns here, what have we got? Let's see. When we look at the columns, we've got TTFF falling under P and TFTF falling under Q. Those together give you a kind of a conventional arrangement of all the four possible ways things could be true or false together. All right, so what if we had 3? If we had 3 variables for declarative sentences, P, Q, R, then we're going to have to represent all of the possible combinations of truth values falling under each of the 3. So in this case, we have also a conventional strategy for representing them. So we'll have the 4 T's and 4 F's. 2 T's and 2 F's. 2 T's and 2 F's. And then we've got T, F, T, F, T, F, T, F. So notice, once you've got, in the third case here, for the third declarative sentence, R, we're just basically alternating true, false, true, false, true, false, true, false, true, false, true, false. By setting it up this way, under P, for example, you've got 4 T's, 4 F's, 2 T's, 2 F's, let's say 1 T, 1 F, 1 T, 1 F, and you can be pretty sure that you've caught all of the possible ways that they can be true and false together. So this is just a simple matter of combinatorial possibility, and you can confirm it for yourself by trying to come up with a possible combination of truth values that doesn't appear in this table and see what you have. Well, you won't find one, in fact, so we can be pretty sure you won't find one. So how about for 4 statements, P, Q, R, S? All right, so then we've got a list of 16 possible configurations. So falling under the P would be a column consisting of 8 T's and 8 F's. Falling under the Q would be a column consisting of 4 T's, 4 F's, 4 T's, 4 F's. Falling under the R would be a column consisting of 2 T's, 2 F's, 2 T's, 2 F's, 2 T's, 2 F's, 2 T's, 2 F's. And then falling under the S at the end would be a list of 16 truth values alternating TF, 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 or whatever. All right. So that's going to look something like this. Actually, this falls off the bottom of your of what you can see, but so you're going to miss there's stuff down here that you're not going to be able to see. But so it goes. Let's see. We've got 8 T's, 8 F's. You're not able to see the rest of them, etc., etc., etc. And there's no possible combination of truth values that fails to be included. So it's 8 T's, 8 F's, whoops, mistake. And each of these are times 2, and then TF, 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 blah, 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 16 of these guys. Okay, so the idea is you're going to try and exhaust all of the possible combinations. So you get the idea. If there are 2 truth values, then the number of possible combinations is 2 to the n. This should be an exponent here. So that should look like this. 2 to the n, where n is the number of statements. So for a single statement, there are 2 possible configurations of truth and falsity. For a pair of statements, there are 4. For 3, there are 8. For 4, there are 16, and so on. Okay, all right, so 2 to the n will give you the list of possible configurations of truth and falsity. N, of course, is the number of statements, the number of declarative sentences. Whoops, you missed the bottom part of that one as well, but sorry about that. We'll move on. So let's talk about AND in more detail then. So what we're going to do now is define AND in terms of the truth tabular representation that we've started looking at. So as we've seen, we're going to, just as a matter of convention and convenience, let each of the declarative sentences be represented by lowercase letters from the end of the alphabet, so P, Q, R, S, and so on. And we're going to take the English word and represent it with a dot. Sometimes you'll see an upside down wedge like that. But for us, we'll use the dot. So what we're going to have then is that P dot Q would be read as P and Q. So that's just a notational point that we're going to use this dot as the and in our logic. Okay, so now we know that P and Q has 4 possible ways of being true or false. So P, Q, those 2 declarative sentences, P, Q, can be true or false together in 4 ways. Why? Well, we know that the set of possible configurations is 2 to the n, where here n is 2, n is the number of declarative sentences. And so, okay, so what do? Well, we just lay out our conventional set of truth values here, right? So we just do it this way. So we've got TT, FF, TF, TF. All right, so now what we're going to do is define AND for all 4 cases. So what we're going to do is we're going to figure out what AND is in each of these scenarios. So what's AND in 1, what's AND in 2, what's AND in 3, and what's AND in 4. So, and if we can stipulate what AND is in each of these, then there's no other way that things can be true or false together. In the case of a logical operator like AND that joins 2 declarative sentences, then if we can define what the truth values are for all of those possibilities, then we're done. Then we've given a definition of AND. So let's go ahead and do it. And we're going to just depend, again, on the truth table here. It's not going to match perfectly with the semantics of the ordinary English word and. As we've seen in the text, there are cases where our English word and doesn't match perfectly with the logical operator, the conjunction operator. But right now, I don't care about that. You shouldn't care about that. You should just look at how we're going to set up the truth table for and see how it gets defined. So let's take a look. So there are 4 possible ways. 1, 2, 3, and 4. And we'll try and stipulate for, well, we will stipulate for each of them what and is, what the truth value for and is in each of these cases. So in case 1, here we've got, if P is true and Q is true, then the sentence as a whole is true. That captures what we, roughly, what we mean by and, the semantics of and in English, and it's certainly what we're going to do here. So in case 1, P and Q, this whole thing, is true. Okay, it's true when case 1 is. So what is case 1? Case 1 is when P is true and Q is true. Let's take a look at case 2. Here in case 2, we've got P is true and Q is false. This is going to be a case where the sentence as a whole is false. Okay, so in case 2 being when P is true and Q is false, we say that P and Q, this whole thing, the composite, the conjunction, is false. So the conjunction is false when one of the conjuncts is true and the other conjunct is false. One more time. The conjunction is false when one of the conjuncts is true but the other is false. Let's look at the third case. In the third case, we've got something similar. We've got one of the conjuncts being false, the other being true, so we say that the sentence as a whole, right here, is false. So this whole sentence, P and Q, so P, oops, and Q, that should be a dot. Let's do it nicely. P and Q is false when P is false and Q is true. And then finally, better be false in the fourth case. The fourth case, P is false, Q is false. Then we say the whole thing is false. So what we're saying here is P and Q is false when P is false and Q is false. Okay, so let's look now at what we have here. So we've got, at this point, let's see if I have a slide for this. I don't. Okay, at this point, we've got a, let me get a new color here. At this point, what we're looking at, falling under the and, the dot, is a definition, right? It's a list of truth values such that it stipulates what's the case in all possible configurations of truth and falsity for 2 declarative sentences. So, given any 2 declarative sentences, we now know that the conjunction of those declarative sentences is true when both are true, this first case, and false in all other cases. Okay, good. All right, so let's move on. So note that there are 4 possible ways of being true and false for P and Q, that the definition tackles all 4 and gives you TFFF. So TFFF is the definition of and. Okay, So now what have I got here? I've got a negation. What am I doing with that? I've forgotten what the next slide will be. Okay, so now let's say you were negating, there we go. So you're negating all of this. So how about, so now you've got the value for P and Q right here, and then you're asking, what about not the case that P and Q? What are the values of this bigger sentence being not the case that P and Q? So how do we evaluate the negation of P and Q? So what we're going to do at this point is, here we've got the symbol for negation. In the text, what I use is this little guy like that, tilde. But a minus sign is fine for this purpose. What we're going to do is say, okay, so we're going to negate this entire sentence, P and Q, generating a new sentence. And you can probably tell that the negation of P and Q will be such that for every time you've got a T, you'll get an F. Every time you get an F, you get a T. So you've got false, true, true, true. So let's go through that slowly, though. Or maybe not so slowly. False, true, true, true. So the negation of this whole thing here, how would we do it? Well, we'd first lay out our conventional ordering of trues and falses here under the P's and the Q's. Then we'd evaluate the truth table for the conjunction right here by looking, okay, TT, T, TF, F, FT, F, FF, F. And then what we're going to do is take this and give its negation. So negating the red means sort of negating the entire sentence, the entire conjunction here. So once we do that, we simply flip the values. T becomes F, F becomes T, FT, FT. So that finally we end up with the value for the whole sentence here. So the value of the entire thing, the value of this entire thing up here, this whole thing is this guy. So this column gives you the value of the whole thing. So if we wondered, okay, well, what are the possible ways that not the case that P and Q can be true or false? Well, we'll say we've got 4 possible configurations of P's and Q's. We've got the value for the conjunction. The negation for the value of the conjunction gives you the following. It says in case 1, not the case that P and Q is false when P is true and Q is true. It's true in all other cases. So take a look at that, and you can pause the video here and study that if you'd like. Of course, I've messed it up a little bit, but all right, so a conjunction then we'll say is false if any of the 2 or more statements joined by the and are false. So if any of the conjuncts are false, then the whole thing is false. So Manitoba is in Iowa and Sonora is south of Arizona is false, even though Sonora does happen to be in to the south of Arizona. So in this case, we'll say that the conjunction as a whole is. We'll have lots more to say about this, but I think the video's run a little long, so I'll pause here.